So what is temperature? It's easiest to start really by clarifying what temperature is not. It's not necessarily related to how hot or cold something feels. On a morning when the wind is calm, I can walk out onto my driveway to pick up the newspaper wearing only shorts and a t-shirt and not feel terribly cold, even if the thermometer reads 20 degrees Fahrenheit. But I would never voluntarily jump into a swimming pool at even 40 degrees Fahrenheit. On the other end of the scale, I could comfortably sit for a while in a sauna at 195 degrees Fahrenheit, which is a pretty high but still not unreasonable temperature to have a sauna heated to. But if I were to stick my hand into a pot of water at 195 degrees Fahrenheit, I would immediately suffer second-degree burns. So the point here is that temperature does not necessarily directly relate to how something feels or how quickly something can be heated or chilled by a substance having a particular temperature. So what we have to do is start from basics and talk about what temperature actually is. Temperature is the property of a substance that determines the direction in which heat is conducted when two bodies are brought into thermal contact with each other. So if you bring something together with something else and heat flows between them, then the direction that heat flows is an indication of the relative temperatures of those two bodies. Get a little bit more specific and say if heat conducts from object 1 to object 2, then object 1 is by definition at a higher temperature, and so we're referring to T1 as the temperature of object 1 and T2 as the temperature of object 2, and so here T1 is greater than T2. Graphically, we can look at it this way. There's our body T1. It could be a block of metal, it could be a block of rock, it could be a parcel of air. It doesn't really matter as long as it's matter having a temperature T1. We bring it into contact with another body at temperature T2. And we observe in this case that heat is flowing from T1 to T2, which tells us that the temperature of body 1 is greater than that of body 2. But what is heat? The definition of heat is surprisingly tricky, and it's easy to get it wrong. The important things to remember are the following. Heat is energy, and it's measured in joules in the SI system, or in calories, or in BTUs, depending on the context. Heat only exists for the purposes of this course, and in many contexts related to thermodynamics, heat only exists in the process of adding energy to or subtracting energy from an object or substance. So an object does not have heat, but heat may be exchanged between two objects. Heat is energy added to or subtracted from an object that does not directly change the macroscopic kinetic or potential energy of the object. Instead, the addition of heat involves the excitement of chaotic molecular motions. This occurs through collisions with other molecules, chemical or nuclear reactions that release heat, the absorption of sunlight, or other radiation, and what have you. All of these processes have the effect of basically increasing the intensity of molecular motions. So here's some key facts. First of all, just to repeat, temperature determines the direction of heat flow when two objects are in thermal contact with each other. Heat will never spontaneously flow from a colder object to a warmer object. This follows from the second law of thermodynamics, which is actually covered briefly in Chapter 6, but I'm just mentioning it right here as kind of a sneak preview for that material later on. The rate of heat flow, which is different than the direction of heat flow. The direction is determined only by temperature, but the rate of heat flow is determined by additional factors. Now, when we talk about the rate of heat flow, we're talking about joules per second in SI units, which also is the same as watts. So if we say 10 watts of heat flow, we're talking about 10 joules per second of heat being transferred from one source to another body. What does determine the rate of heat flow is the magnitude of the temperature difference, or maybe if you want to get more rigorous and start looking at things on kind of a very local level, we're looking at the gradient in the temperature, that is the change in temperature per unit distance, but we're just going to say temperature difference for now. It also depends on the area through which the heat is flowing. If you have a larger surface area between two objects of having different temperatures, then there's more heat flow through that larger area. Additionally, the thermal conductivity of the material matters. If it's a very conductive material like metal, heat can flow rapidly. If it's an insulating material like styrofoam or the fiberglass wool inside your walls, then for the same temperature difference, you may not get very much conduction of heat, but it will still be in the direction or from high to low, and it generally will not be zero. And finally, if you have something immersed in a fluid, and the fluid has one temperature and the body has a different temperature, then the strength of any fluid motions will change the rate of heat exchange or increase it for higher fluid flows. And this is the essence of the idea behind what we call wind chill. If you go outside on a windy day and it's 20 degrees, you're going to feel a lot colder than if you go out on a calm day at the same temperature of 20 degrees. Let's talk briefly about thermal equilibrium. In general, heat will continue to conduct as long as a temperature difference persists. But heat transfer, if it's not countered by another process, acts to reduce the temperature difference. So the warmer object cools by losing heat. The cooler object warms by gaining the same heat. Given enough time, the temperature difference will decrease to essentially zero. That is, heat flow will cease, the objects will wind up with the same temperature. Graphically, we can look at it like we did before. There's our two bodies with heat flow from object 1 to object 2. We've already said that in this instance, the temperature T1 is greater than T2. But the result of this process is that you're going to be taking heat out of T1, out of body 1, and lowering temperature T1, and adding heat to the second object, which will warm it and cause the temperature to go up. And eventually, equilibrium is reached when the two temperatures are the same and no more heat flows. There's an application that is actually quite important, and it's useful in a lot of different contexts, including how much heat loss you have from your house. But in the context of meteorology, you might be interested in the question of how long it takes for something like a thermometer to equilibrate to the environment when you take it outside into a warmer or hotter environment than you had indoors. The specific relationship given by Newton's law of cooling is that the rate of heat transfer is usually more or less proportional to the temperature difference, and because that heat transfer is proportional to the temperature difference, the rate of change of the temperature difference itself is also proportional to that temperature difference. Mathematically, we can say that the derivative of delta with respect to time is equal to minus some constant times delta. Delta is the temperature difference, and delta becomes smaller as heat flows, and that's why we have a minus sign in front of the right-hand side there. That means that the temperature difference will decrease with time as long as nothing is going on to try to maintain that temperature difference. And that implies in turn that eventually that difference will decrease to zero. But it does so at a rate which is proportional to the current difference. So the closer it gets to zero, the closer the two temperatures get to being the same, the less rapidly the temperature changes. That's why we have the delta on the right-hand side as well. The constant C, it depends on the specific situation. If you're talking about, say, a can of cola that you set out on the counter after it's been in the refrigerator, and it takes quite a while for it to come up to room temperature sitting out, whereas something much smaller will reach room temperature a lot more quickly. Anyway, this is called Newton's law of cooling, and as I said, it's quite applicable to a lot of important practical applications involving temperature and heat. So the real-world example that I'll allude to right here, and I'm not going to solve it here specifically, but I will use this as a basis for some discussion in class, is that you can take a thermometer that has its own temperature, which we'll call T-therm just for short, and we're taking it outdoors to expose it to the environment, which is air, and that air temperature is T. Now we're going to assume that the air temperature does not change. In other words, even though the thermometer is giving up heat or taking up heat in exchange with the atmosphere it's small, but the atmosphere is large, and therefore the atmosphere doesn't really respond to that exchange of heat by changing its own temperature much, whereas the thermometer will come eventually into equilibrium with the atmosphere. So the temperature difference is delta, as I said before, which in this case is just T of the thermometer minus T of the environment, and T of the environment in this case would be essentially a constant for the time that you're taking, say, a weather observation. There's Newton's law of cooling again, saying that the rate of change of delta is going to be minus some constant C times delta. And as I already said, we see that the thermometer will eventually correctly measure the environment's temperature, but it won't do so immediately. It takes time. Here are the things that I'd like you to think about in preparation for a little discussion about this in class. First of all, what do the physical dimensions of that constant C have to be? We already said that it controls the rate of heat exchange. So what are its physical dimensions? I'd like you to think about physical dimensions whenever you can. When looking at something mathematically, what are the physical dimensions of each of the terms appearing in an equation or an expression? The second thing is, what would a graph look like? A graph of the temperature difference, delta, as a function of time. And finally, and this is getting into differential equations, as it turns out, because that is a differential equation. How do we formally solve the equation to find an explicit expression for the temperature difference as a function of time? So we're going to look at the relationship between temperature and kinetic energy. What is happening in the substance or the object that gives it a particular temperature? It turns out that that's very closely related to kinetic energy. Now we know what kinetic energy is. It's energy of motion. And you probably know from high school physics that the kinetic energy, which here is Ke, is equal to 1/2 times the mass, m, times the velocity squared, or the speed squared. Velocity is a vector, speed is not a vector, so we're going to say speed here. We usually apply that definition to macroscopic objects. You can throw a baseball or fly an airplane or drive a car, and each of those moving objects has kinetic energy, which is given by its speed squared times its mass, and then divided by 2 gives you the kinetic energy in joules. But an object can be stationary and still have kinetic energy at the level of individual molecular motions. So the definition is that absolute temperature is proportional to the average or mean kinetic energy of the molecules in an object or substance. We'll look at that slightly mathematically here. The absolute temperature T is on the left. That little symbol in the middle there is a proportionality symbol. We're going to say not equal to, but is proportional to the mass of the molecules times the mean squared velocity. So the bar over the top means take an average of everything underneath the bar. And under the bar we have a v squared, which is the squared speed, I should say here. And if you take the average of the squared speeds of all the molecules in your substance and multiply by the molecular mass, you have something which is proportional to absolute temperature. That sounds complicated, but it's not really that complicated. The important thing to keep in mind is that molecules have mass. They also have speeds. They don't all have the same speed, but if you square their speeds and then take the average of those squared speeds, that's the thing which is proportional to the kinetic energy of the molecules and thus to the absolute temperature. So the key takeaways here are that absolute temperature cannot be negative because neither mass nor squared velocity can be negative. In the classical or non-quantum approximation, an absolute temperature of 0 implies that all molecular motion has come to a stop. Now that starts to break down when you get into quantum physics. I'm not going to worry about that. It's not important for this class, but nevertheless, absolute 0 does serve as a lower limit to the temperature that any substance can have. And then a final, slightly more I guess, nuanced takeaway from that is that a gas with a small molecular mass will have a higher mean squared molecular velocity than a gas at the same temperature with a larger molecular mass. That just means that for the same temperature, a light molecule like helium will be moving on average with a higher speed than a heavy molecule like, let's say, methane or something, or even just nitrogen or oxygen are heavier than helium. And that in turn implies that helium and maybe hydrogen atoms, when they're present, are more likely to have enough speed to actually escape from the top of the atmosphere just because of their thermal energy. They simply are moving faster than the heavier molecules. And it is true that we are actually losing gases like helium and hydrogen to space through this motion all the time. To summarize, in this module we covered the following topics: the physical meaning and significance of temperature, the form of energy that we call heat, thermal equilibrium and Newton's law of cooling, and the relationship between temperature and molecular kinetic energy.